this is basically where we ended up last lecture, okay, on Friday. Okay, everybody survived the weekend? Great weekend. You guys get out there? Yeah. This is my David Letterman start. Okay, slowly work you guys in there. Okay, so where we ended up last week was with the architecture. We were talking about texture. And we were saying, you know, we have these coarse fragments, everything larger than 2 millimeters. And the gist of the message there was, well, the reason we have these, we break up soil texture with smaller components and larger components is because of that interface. Okay, if you think about a volume, and you start making things smaller and smaller and smaller in that same volume, the surface area in that volume increases dramatically. All right, and that's where I showed you this slide. This slide, remember this slide? Okay, so here's the same volume, and I start putting smaller things in that same volume, the surface area increases. Now, if you remember from the very beginning, I wanted you to think of these soils as a volume. Why? Because this volume is an interface of both solid and void space. Okay? It is the interface between the hydrosphere, the lithosphere, the biosphere, and the atmosphere. Okay? And it's at these edges that that interface happens. So the powers to be basically said around 2 millimeters, if you're smaller than 2 millimeters versus larger than 2 millimeters, these interactions are so dramatically changed at 2 millimeters. Those are the particles that we're going to actually look at as being important for soil texture. Everything else we just call coarse texture, coarse particles, gravel, boulders, that type of stuff. It has a huge influence on drainage and bearing capacity, but it has a very small impact upon biological and hydrological interactions. Okay? And that's why we have this 2 millimeter. And I threw this slide up here sort of to show you that basically everybody sort of agrees that that's 2 millimeter. Whether you're the Brits or the United States, or the Ag Department or the engineering groups, or even the one, I didn't tell you this. I have dyslexia, so just be aware that words are going to come out strange every once in a while, besides the fact that I talk fast. Okay, so the International Society of Soil Science. Okay, so those are the geeks that say this is what it is. Okay, so we all agree that's this 2 millimeters. Okay, now the cool thing about this is that we start talking about these things that are under 2 millimeters. We basically have 3 different size fractions. The largest is sand, then silt, and then it's clay. Sand tends to be round. Silts and clays tend to be disc-like. And that has to do with the nature of the mineralogy. And we'll talk about that later in the semester. But at this point, I want you to realize they have these distinct shapes and sizes. Now, one can certainly imagine that if I look at a pile of dirt or soil in situ, here's a monolith, okay, that this is not pure sand, silt, or clay. There's a mixture of it. Okay? It's that mixture of these soil separates, sand, silt, and clay. It's the mixture of these soil separates that we actually call soil texture. Okay? I'm sure everybody has heard the term soil texture before, but these are the soil textures. And depending upon the combination of sand, silt, and clay, you will have a particular soil texture. Okay? These graphs, you basically read them up. This is clay, so this is 0 to 100% clay. This is silt, that's 0 to 100% silt. And this is 0 to 100% sand. Okay? You look at the arrows to follow which line path you're going to be following. So if you're looking at percent clay, you follow it this way. If you're looking at percent silt, here the arrows are pointing this way. Okay, if you're looking at sand, you're following it this way. You technically only need to know 2 of these to be able to figure out what the texture is. Imagine that I have 40% sand. Oh, I'll make it easier. 30% sand. This is my line for 30% sand. And I have 40% silt. Follow that line down. They meet right here. What's my texture? Clay loam. Does that make sense to everybody? Okay. Now, the combination of these textures thereof together basically make the textures. In general, the sandier soils are the coarser soils. They tend to be the sands, the loamy sands, the sandy loams. Okay, we go back to the texture triangle. Where do those guys sit? Sort of down here. And if you look at it, we're looking at 50% sand or more. Make sense? We follow this through the loamy soils. Loam is basically the moderate, the intermediate of everything, a mix of everything. Everything from the fine sandy loams all the way to the silty clay loams. Okay, when you get down into the clay loams, you're looking at predominantly clay dominated soils. Okay, go back to that textural triangle. The clayey soils up here, the silty soils here, the sandy soils here, the loamy soils in the middle. Make sense? Right? Questions? Pretty straightforward. Okay. This gives you an idea of what the particle diameter on. This is sort of geekish stuff, but just to give you an idea, just so you know that just because it's a clay doesn't necessarily mean it's 100%. There could be a mixture of it. It could be, in fact, up to 60%. And if we go back to the textural triangle, if I have 60% clay, I'm considered a clay. Okay, I don't have to have 100%. I could be 60%. There could be 40% of other stuff. In that scenario, the clay is so dominant that it doesn't matter if it was 40% sand. It is a clay. Now, to give you a sort of a little story to sort of give you an idea why this is important. In the 70s and 80s, the landscape people were working on ballparks, baseball fields in particular, and they were trying to increase the drainage of the ball fields. You can imagine if it rains and the ball field gets soaking wet and the water doesn't drain, it basically really screws the people that are playing the sports. Okay, so the thought was, well, if they're not draining, what should we do? Well, let's add some coarser material. So what they started to do is they started to add sand. What do you think happened to those ball fields? It actually got worse. Why? Besides the fact that we're making cement, but why?
I was going to say that you're making cement.
You're basically making cement. Well, think about it. What's going on here? They were not adding a lot of sand. They were just adding 20, 30% sand, thinking that that's going to make a dramatic change. Remember me showing this slide before? Okay, these particles can pack a lot of different ways. If I have a uniform particle, same size, they can pack like this, or they can pack like this. But if I start mixing materials, these cracks can start getting filled. So imagine I put sand into this ball field. What's going to happen to all these little cracks? They're going to start getting filled up. And if I start filling up these cracks, the water's not going to flow anymore. It turns out that if you wanted to increase drainage in these ball fields, you'd have to add like 70 to 80% sand. If I've got this much volume and I'm adding 70 to 80% sand, my ball field is now this tall. That becomes a problem for a lot of ball field designs. Okay? That's why this is important. Okay? Questions? No? We're cool? Okay, so far I've been basically just talking about the individual particles. Well, you guys have played with clay, hopefully. What happens to it? Do you actually have an individual particle of clay in your hand when you start making pots? It's a clump of stuff, right? These textures, these individual particles join and grab to each other. And they create what we call aggregates. The smaller the particle, because of those surface areas, the smaller the particle, the tighter the bonding. The tighter they'll hold together. That's why clay is so sticky. And sand, on the other hand, you can run through your fingers. Now what happens to sand when it's dry and you just pour it in your hand? Sort of pours off, kind of like salt or sugar or something like that. What happens when you start adding water to it? Does it pour as easily? No. So the water content has a huge component to this as well. Now imagine that my soil is being grown in organic matter as well. I have plants growing on top of it. So it's not just the mineral component, sand, silt, and clay. I start having organic matter in there. Is that going to start helping putting things and holding them together? Okay. These are called aggregates. And these aggregates basically act as larger particles and as smaller particles at the same time. Okay. Here is coarse grain sands. You can see the individual, they're sort of rounded. Okay. These are clay aggregates. They're clumping together. They're basically the same shape. They're sort of acting like they are sand. Okay. There's large pores in between them. But they are also made up of tiny little pores, lots and lots of little pores. Okay? And those little pores basically act like the clay that you were playing with as a kid, or making clay pots or pinch pots or something like that. Does that make sense? Now, here's the story that goes with that. When you guys were kids, or where you guys are in the cafeteria this morning, and you guys had a straw, and you put it into your drink, and you pull the straw out, at the bottom of the straw, there's always that little drop of water, or soda, or coffee, or milk, or whatever it happens to be your choice. Okay? What happens to that if I had put a smaller straw in there?
Should it go higher up?
It should go higher up, right? Does that make sense? If I have a big straw, here's my pipe, really big straw, I put it into the glass, I bring it back out, I'm going to have a little drip of water down at the bottom. Right? Does that make sense? And goes up about this far. If that straw gets smaller, that drip of water is going to go higher. And if it gets really small, that drip of water is going to be really high. So I'm progressively moving up the height of my straw. Does anybody know what this is called? This is called capillary action. Okay? Well, imagine what's going on with these guys. I have two different straws there. I have a nice large straw in between, and then I have lots of little straws in here. So these aggregates are going to behave both as a large straw and as a small straw, which means they're going to affect the interfaces, and they're going to affect water storage and water movement. Okay, does that make sense? It's sort of, kind of? I'm already losing people? No? Okay. So we move on. You've seen this slide before. Let's talk about these different types of soil structures. They're not all these sort of P-shaped objects. Okay? Depending upon this shape, I can have different effects. We have a number of different ones. We have granular, we have blocky, we have things that are called prismatic. We have single grain, which is sort of structureless. There's no structure there. We have platy, and then we have columnar. Okay, let's start with the granular ones. The granular ones are really what they sound like. They're like cookie crumbs, grains, grams. Okay? Okay, they're rather small, about the size of maybe my pinky, or the top part of my pinky. If they start getting bigger than that, we start calling them blocky. Okay, they're rounded. Okay, they're generally found at the surfaces of the soils, because these structures are generally made from accumulation of organic matter and roots, sort of holding things together. Okay? The next one over are blocky. You find these generally farther down in the soil. Okay? These are generally made from pressurization, expansion, contraction. Okay? When the soil starts expanding, when it gets wet, the soil is going to expand just like a sponge, and it's going to create pressure plates, and it's going to squeeze things. And then when it gets dried, it's going to start crunching up. Okay? It's going to start contracting, and you create these sort of like larger crumbs. You'll see these. Then we have prismatic ones that are literally like tubes. And then we have columnar ones. Those are also like tubes. The prismatic ones sort of have sharp edges. The columnar ones are really sort of rounded. Then we also have platy. Okay, platy are kind of interesting because you can find them high up in the profile, and you can also find them very low in the profile. Does anybody know what a desire line is? Any LA people in here? Landscape, not Los Angeles. Landscape architecture? Okay, I know all of you guys have walked on the ag quad, right? Have any of you guys walked on the ag quad off of the sidewalk? Those you found a spot that is desirable to walk, sort of a shortcut rather than following the path. And a lot of people do the same thing, and you start creating what's called desire lines. Those are those sort of, okay, here's my sidewalk going like here, and I'm going to cut it off. Okay, what do you think is going to happen to the soil underneath? Slowly gets compacted. Okay, and if it's compacted, the pressure is always going this way. It's not going to be doing anything else. It's always going to be going like this, down, 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 down. And what happens is the soils get pushed this way, and you start getting platy behavior. Now, those desire lines are often very difficult to grow plants, right? Obviously, we're crunching the plants as we go across. But what else are we doing? Well, if we create these platy types of structures, what's going to happen to the plants when they try to start volunteering back into that area? They're not going to. If I keep compressing the material, I'm making it denser and denser and denser, and I'm also orienting it this way. Okay? So if a root wanted to get through here, it's going to have a hard time breaking through. So what it's going to have to do is it's going to have to find a crack. So the roots are going to have to go way over here to go down a crack, and then back and forth. Does that make sense? Okay. Now, can you guys think of any other scenarios that would create this type of structure? Oh, question, go.
Oh, no, I was going to add to this overgrazing of cattle.
That actually feeds right into my next question. Can anybody think of another scenario where this type of structure would become? And the answer was overgrazing of cattle. Okay, so imagine, I got my feed bucket right over here, and I got the desire lines of the cows, or I only have a certain amount of grass on my turf, okay, and the cows are just basically killing off all the grass because they're eating it, okay, and I never get any sort of organic matter sort of pushing in, creating these other types of structure, these granular structure. Okay. Anybody been out west and taken a look at some of the hillsides out there, and they look like they have fairy rings around them? Has anybody seen this? Okay. Cows, and most ungulates in general, are not very good at going straight up and straight down hills. So they tend to graze around the hills. Okay, and you can see these rings as you go farther and farther out west because it's drier and drier, so they have less vegetation. Becomes very pronounced. Those paths, they've basically created desire lines, and they will follow these paths forever. Okay, that's what the structure is right underneath. Okay, any other ideas about where we could get that kind of structure?
You could run a tractor through the same spot.
Tractors, mechanical vibrations and tractors. Tractors are direct pressure, but also you can get it from mechanical vibrations. If you have a truck driving down a road over here, because of the vibrations over here, you start settling your soil, and you'll get the same sort of structure. Okay, tractors do this two different ways. One is the tread of the tire, but also if they're pulling equipment behind them, like a tiller or some sort of mow-bore plow or something like that, that mow-bore plow can actually create a platy structure subsurface. Okay, so they're breaking up the soil up here, but the bottom of the plow is running here. The tractor itself is way up here. The bottom of the plow is running here, and they'll create these platy structures. The last structure really is this sort of single-grain structureless material. And there's two different kinds of them. One of them is really this sort of, I pull a hand to pull out and it just sort of pours out of my hand. And then you'll also get these sort of massive structures where the whole unit is sort of one structure. You get this in a lot of clayey soils where depending upon where you stick your hand in, you pull it out, it holds together. But if I pulled my hand, if I moved it just a little bit, even overlapping where I was and pulled it out, I get this sort of massive structure. Sort of like clay, right? You pull a piece of clay out. Depending on where you put your hand in, you can pull a piece out. Does that make sense? Yeah? Okay. Questions on this so far? Okay, so why am I introducing this when I'm introducing textures? Okay? Why any ideas? Why would it be I'm talking about textures. We're talking about soil architecture, and I introduced the idea of textures. Why would I also introduce the idea of soil structure at the same time?
The structure determines the texture.
Actually flips the other way around. This texture, actually, maybe you said that right. Did you say the texture determines the structure or the structure determines the texture? Let's take the benefit of the doubt. Let's say you said it the right way. The texture does, in fact, impact the nature of that structure. If I had sandy material, it would not be that easy to make this kind of structure. Okay? If I don't have organic matter, which is not a texture, if I don't have organic matter, unless I have clay, it's going to be very hard to make this structure. Does that make sense? Okay, so that's why we're introducing these things at the same time. And the other component of why I'm adding these things at the same time is this is the interface these structures and the individual textures and the individual soil particles determine the nature of that interface between the solid part of the soil and the void part. One can certainly imagine if I have this kind of structure versus this kind of structure, I'm going to have a very different interface. Correct? Does that make sense? That's why we're talking about it at the same time. All right, so let's go on. I throw this slide up here every year and I say I'm never going to do it again because you guys can't see anything. But on the side, I put this up here because these are some really cool slides of what these things look like in the real world. But I think we're going to have best by actually seeing you seeing them in the real world. They have a little better graphics over here, but it gives you an idea of what these things look like. Okay. Now, here are those textures again. But in this scenario, we're basically looking at how water flows through the system. Okay. Single grain, rapid movement. Okay. Blocky, these larger granulars. Very moderate movement. Platy, water hits the top, it moves through very slow. Does that make sense? This would be very fast, this would be very slow. I mean, if you think about it, it hits the ground, okay? And if I have lots of individual grains, yeah, my pathway to get down is going to be like this. It's going to be a little squiggly, but if I hit the platy structure, the pathway for the water has to go like this to move down. Does that make sense? So just by the architecture, let alone thinking on top of that, there's going to be a density issue here too. Because if this has been squeezed together, the pathways, the pipes where that water is going to be flowing is going to be smaller too. Go.
What's the scale of the blocky and the single grain? Because I feel like blocky should drain faster than the smaller one.
Oh, well, I understand the question. The scale, I can give you the scale right here. No, I can't. Where's the scale stuff? I don't have the scales on these one. But basically, you're looking at up to 5 millimeters. Okay. Here, you're starting to look at things up to fairly large size. Okay. Platy can be as thin as this and as wide as that, or up to significant, massive materials. And I don't mean massive in the sense of the texture or the structure. Okay. Here's the granular stuff. The granular basically behaves similar to the single grain. The prismatic behaves fairly similar to the blocky. Prismatic has large pipes within them, or between them, I should say. Within them, the water's not moving very fast. But between these structures, there's gaps, and the water will move down it. Okay, massive, not single grain, but this is, remember when I said massive like clay balls? Okay, massive is going to be very slow in its transportation of water. Okay, now, the way we've shown it here, it's like a rain event. Okay, but you got to realize that water moves in all different directions. This could actually be an aquifer type of thing where we're looking at an artesian effect where the water literally could be going this way. Okay, often the water is going to be moving this way through a landscape because of hill dynamics. Okay, it's top of the hill, bottom of the hill. Rains up here, infiltrates here, the water is going to be moving laterally through the landscape. So all of these are going to be looking at water movement in multiple directions. Now this is sort of the simplified schematic of it. Okay, here is the small pipes. Here are the large pipes, or the large pores and the small pores. These could be single grains, or these could be aggregates. Okay, but you can imagine where the water is going to be moving. Okay, the water is going to move fastest in the larger pipes. Make sense? It's going to be moving slower and slower as these pipes get smaller and smaller. Okay, so you have a rain event. Where's the water going to be going? Around here it's going to be going down, right? Water is going to be moving into the soil. It's going to preferentially be moving in these larger pores. Okay, as the water moves down, capillary action is going to suck water into these smaller pores and hold it there. Now, if you have a torrential rainstorm event, you might overrun or put more water in than the capacity of the pipes are, at which point the water will fill all the way up to the top, and then you'll have overland flow. Okay? But this soil will absorb as much water as it possibly can, and transfer as much water as it possibly can. Transfer is moving the water through, sorbing or absorbing is holding the water. Okay? So you basically have two sort of water movements here. Storm stops. Rain stops. What's going to happen with the water? Capillary action says that the pipes are going to hold as much water as they can against gravity. I mean, this is the straws. As the straw gets smaller, it's going to hold more water, right? These large pipes are going to drain out. The small pipes are going to hold the water. Okay? Key point here, what's going to start moving through these large pipes now? Air. That is that void space of these soils. Remember me saying these void spaces are extremely dynamic? The dynamic nature of those void spaces are strongly controlled by the solid part of the soil. The nature of the solid part controls the nature of the voids. If I have lots of small voids, I'm not going to be transferring a lot of water, but I'm going to be storing a lot of water. If, on the other hand, I don't have a lot of small pores, I'm more like a sand, I'm going to be transporting a lot of water. Does that make sense? This is why aggregates actually become very, very important. In the scenario where these are individual grains of sand, I only have these interfaces between the sand holding the water. But if this was a clay aggregate, all of those little pipes that were inside these aggregates are also going to be storing water. Does that make sense? Yeah? Questions so far? We cool with this? So the take-home message here is the pores themselves. The pores are the result of this solid component. The solid, whether it's the individual particles or the aggregates. Small pores hold water well. Hold water well. Okay? But they also, because they have water in them, are going to restrict aeration. They're going to prevent air from moving into the system. Large pores hold water poorly. Lots of transmissivity, okay? But they are also going to prevent really free airflow. And this is the take-home, sort of me hitting the same spot again. Soils are these three-phase systems. Okay? They're the interface of these four spheres. They connect the soil air, the soil solution, and the soil solid. It's that interface that drives all of these reactions. Okay, we good with this? Guys think you've survived? Comfortable? All right, so this is where I was supposed to have ended last lecture. Okay, so right now we're going to transition very quickly into the next lecture. Which begins with a review of the last lecture. No, so we're going to skip this part, but basically you have an understanding of this. This is that soil volume. Now we're going to be coming back and we're going to start talking about bulk density later on. But right now, because we're going to be going out to the field today, I wanted to talk a little bit about soil morphology. We're going to go out and we're going to start seeing soils in their natural habitat. We're not going to a zoo. Okay? This is the zoo right here. Okay? This is what's called the soil monolith, and this is basically an excavation of the side of a soil pit. You guys are going to be visiting soil pits. Basically what we do is we dig a trench into the ground and we have a face of a profile of the soil. Okay, and what we do is we basically excavate that out, we glue it in place, and we basically bring it back home and say, and we hang it on our wall. You know, it's kind of like our deer head or something like that. Okay, we call it a monolith. Okay, I'm going to have an exercise for you guys today, and I'll talk about it at the end of class. But basically, you guys have been out in the hallway. You have seen that there's a bunch of monoliths out there. What I'm going to want you to do is go out there and pick a monolith. Okay, I want you to find the monolith for whatever reason, whether it's color, its name, or whatever. It's boring, it's exciting. You guys are going to be taking a look at this monolith, and you're going to be basically writing a paragraph about it. Okay, and in that paragraph, what you're going to be saying is, what do I see? What are the things that I see that may interest you, but what are the things, hopefully they do interest you, but what are the things that I see in that monolith that I think might control what's going on in that monolith soil? Okay? Now, to give you sort of a primer on that, we're going to talk about the different components of these soils. What do they mean? Why? How do we label them? Okay? And this is sort of the slide that we start with. Okay, this is the soil horizons, or the soil morphology horizons, the distinct different layers within the soil. Now the way we introduce this is we basically have individuals and we put them in orientation. We have an O, an A, an E, a B, a C, and an R. There is also a W horizon. Okay? Now, before I get too far in this, I want you to realize that not all soils have all of these horizons. And some soils actually have multiples of the same horizon. In fact, this week you're going to see one of those. Okay, so let's go through these horizons and let's talk about what they are. The first horizon is an O horizon. It's predominantly organic. Can we kill the first bank of lights? I don't think you're going to be able to see this. The one closest to me. Try one more. Can you guys see those? Are you going to be able to see some of these? Yeah? Okay. So it is the O horizon. It's predominantly organic. It's an organic surface horizon. It is not present in all soils. And when you start getting into agricultural soils, these are pretty much gone. Okay? It's an O for organic. It's typically in uncultivated forest soils, but you'll also see them in other types of soils. Certainly you'll see them in wetland soils. It is a dark, rich organic horizon. Okay? The decomposition rates, there'll be at different decomposition stages, I should say, not different decomposition rates, but it is driven by organic matter. It is a horizon that is organic matter. It is not mineral. Okay? Often you'll find these buried as well. They can be buried. There can be a horizon way down deep because something could have happened to have deposited on top of it. Okay? The next horizon down is a mineral horizon. It's an A horizon. It is the soil mineral horizon that has the maximum amount of organic matter in it. These soils can be buried as well. So these horizons, there can be multiple A horizons. Okay? It is the soil that has the maximum organic matter in it, and it is also the horizon that has the maximum biological activity. Mineral soil that has the maximum biological activity. Okay? Because it is close to the surface, where it's close to temperature changes, moisture changes, oxygen changes, it is also has huge amount of weathering in it. Both decomposition as well as mineral weathering. Okay? It is also a zone of, or I should say a zone that is the source of a lot of alluviated materials. Okay, alluviated materials means E is the way to remember this, things that are moving out of this horizon. E, alluviation. Okay? This is organic up here, but you can see this nice zone right through here. You can see this nice, it's dark. It's not, it's dark like it's organic because it has organic material in it, but it's still predominantly a mineral soil. Right below this soil, we have an E horizon. Okay? Sometimes it's found below the O, directly below an O, but it's usually found below an A, around here. Okay? It is a mineral horizon, and it is strongly eluviated. Okay? Eluviation means things that are stripping through it. Things are running through it and it's being stripped. Okay? This is a translocation horizon. Organic acids are leached from above, and they can weather and strip this horizon. You can see this nice, very apparent E horizon right here. Above it is an A horizon with an H, which means humic material, basically accumulation of humic acids. Okay? Below it, it has H, that's organic stuff as well. Okay? This and this, these are really strong, pronounced E horizons. Okay? The color that you see is the result of the minerals that are left behind. Okay? When these soils were first seen, they were basically seen in forests. And people associated this, because of this white color, they associated this with forest fires, thinking that this was ash. Ash, A-S-H, ash. Okay? It was that white, and it is that sort of powdery in these scenarios. And that's why they thought it was forest fires. Turns out that's not the case. These soils, these are two spotted soils, this particular kind of soil we'll talk about later. But these are forested soils, and they're formed in sandier grain materials. Now you guys have been to the beach. What's the color of sand? Sort of a whitish, clear, sort of manila color. That's where these colors are coming from. They're coming from the minerals, not from a forest fire. Okay? But we also have an E horizon right here. Now this is not a forested soil, but you can see my A up here, horizon down below. This zone right in here has been stripped out. The coarser textures stay behind because the silts and the clays will be entrained with the water and they'll move down. The organic matter will move down. Okay? What's left behind is this coarser stuff and it looks lighter. Go. In this horizon, you can see an O horizon up, sort of up here. But in these, there's not much of an O horizon left. Remember me saying there's not O's in everything, and there's not A's in everything, or even E's, but go.
So if the texture's different from each horizon, does water move at different speeds in each horizon?
Yes.
Okay.
In fact, that textural change often predicts where these boundaries are going to be, where you can start seeing this stuff.
How do you tell the difference between the A and the O if they both have a lot of organic matter?
The O is all organic matter. The A is a mineral horizon with organic matter. It's the mineral horizon with the maximum amount of organic horizon, of organic material. If the organic matter accumulates enough, that A will turn into an O. Okay, B is a zone that's right below that E horizon, and it's a zone of illuviation. Basically, I, the way to remember this is in. This is a zone of accumulation. Okay, this is where all that alluvial stuff, eluvial stuff, basically comes down and is deposited. And that's sort of the definition of this horizon. It's a zone of accumulation. So alluvial clays that were entrained by the water, the dissolved irons and aluminums, the organic material, salts, silicas, all that stuff that was dissolved at the top is being moved down by the water. It's being deposited in this horizon. Okay. There are a number of different kinds of them, and you will learn them through the semester. But we're basically looking at, I can't quite see this one myself. We're basically looking at this zone of accumulation down here. Here's the specific kind of accumulation. This is that spotosol I showed you before, a very white horizon here. Organic acids, and what we call S stands for susquioxides, which basically is iron and aluminum oxides that have been created from above, are moving down here and are being deposited here. Okay? Does that make sense? You will see these horizons. Okay? Here's a number of other special sort of horizon. This one, that's not a soil horizon. Okay, but it's okay. See these white spots in here? That's an accumulation of calcium carbonate. Okay, as you get farther and farther west, systems go drier and drier. Calcium carbonate starts accumulating. Okay, and they can accumulate into soil horizons. I don't know if I have another slide of this. I don't. Okay, I threw this one in here because this is basically the same process. Has anybody been to any of the caverns around here? And this is basically, so a couple of you guys have seen this kind of stuff, right? This is basically calcium carbonate. What's happening is there's a whole chemical reaction, but what's happening is the partial pressure of CO2 is shifting from the soil to the cave and from the surface. And what happens is the calcium carbonate basically solidifies. Okay? In this case, this is an extreme case where you're basically creating a stalactite and a stalagmite coming together and making a pillar. Okay? But this is basically the same process that you're seeing. And these are small, tiny little aggregates that are in the soil. But this is a zone of accumulation. It's a diagnostic of a B horizon, accumulation of material. Okay? The next horizon down is the C horizon, which is partially broken down parent material. Okay? Technically, there's not supposed to be any kind of biological activity going on in here. So if you see roots or something like that, you're out of, it's not a C horizon, it's a B horizon or something else. Okay? But in reality, we do often see roots and things like that in here. But basically what we're looking at is parent material, undifferentiated material, stuff that has not been subjected to soil forming processes. Okay? Often you'll have a deposit. Now this is a deep lust deposit down here, so this is a material that's been deposited on something else, older. This C horizon right here, this is the stuff that this is made of. It just hasn't been, the world has not acted upon it yet. It hasn't been subjected to change. Okay? Here's another example of a different type of parent material. You're basically looking right in here. And this is basically a gravel bar. You see all the rounded rocks in here? Okay, this was probably a deposit from a river or something like that, and the soil is forming on top of that from stuff coming above and stuff being weathered away from below. Okay, this is the living soil in here. This is the sea material, so this is the whole soil profile, but this is the soil that's being formed. And this will ultimately move through this, unless something catastrophic happens. Okay, does that make sense with the sea horizon? There's another sort of exposure of a hole. You can actually see CA, you can see everything there. Okay, now I wanted to take a step back and sort of talk about some of the features that are in these soils. Okay, so here is the profile. This is a A, E, B, a couple of B's, a B, a BC, and we'll talk about what these combinations are later on. But what I wanted to show you is where the materials are within these soils. Certainly the first one, organic matter, makes sense. If I have a soil, where's most of the organic matter going to be? Up top, because that's where it's coming in and that's where the organisms are living, right? I mean, I got a plant growing, and around here every fall, I get a dramatic increase of organic matter on my soil, right? Leaves fall. Leaves hit the ground, okay? Organisms start taking that material and using it as food, and most of those organisms live up in the higher parts of the profile, and that's why the organic matter accumulates up there. Now, if I've got a lot of organic matter, that's when I'm going to get an O horizon. But in this scenario, we're looking at a mineral horizon that's enriched with that organic matter. Does that make sense? Okay. How about the clays? What's going on there? You can see that I have a huge bulge of clay farther down. I have a zone here where I'm lost. And then way down, there's not very much. And then I got a little bulge up at the top. What's going on? Any ideas?
Is the clay being washed out of the E horizon and collecting in the E horizon?
Yes, but a little bit more than that. It's not just being washed out, but it's also being washed out of this horizon as well. So it's getting washed out of here, it's getting stripped out of here, and it's getting deposited down here. Now the water is not moving far enough to deposit it all the way down here, and you start getting into, hopefully, the sea horizon. Remember, the definition of the sea is undifferentiated parent material. Stuff hasn't happened there yet. Once this clay starts accumulating down in the sea horizon, this sea horizon won't be a sea horizon. It will become a B horizon, because the B horizon is a horizon of accumulation. Does that make sense? Yeah? Okay. We can look at the same thing with iron. Iron is one of the major elements on the planet. Okay. The same thing is basically happening. This is a particle. This is being transported as a dissolved mineral. Okay. The same thing's happening. Okay. Questions? Go.
Does the A horizon hold more clay than the E horizon because organic matter is so charged?
Yes. The organic matter is, it's not necessarily because the organic matter is charged. The clay is charged particle as well. But it's because that organic matter creates those aggregates, and it holds that material a little bit better. I mean, it's acting like a net. It's not quite, but it's sort of a pseudo net. It's sort of holding it in place. Now, the reality is, if we looked at this clay, when this profile started, all the way to the top, it probably had about this much clay in it. Okay, so this whole line, stuff is coming in, but we're basically looking at redistribution of this clay throughout. So if I took this, I took all this clay, with the exception of here, and I averaged it throughout the whole line, you'd have one line that's sort of like right here. Does that sort of make sense? So it'd be a straight line, straight up. And we're basically just seeing the redistribution of that clay because of the water. Yes? No? Yeah? Okay. Questions? We good with this? Go.
What's the composition of the E layer, the E horizon, that allows it to be leached so much? Like some soils, because
It's generally present in all soils, and it's generally when you look at E horizons, they always have, once they're developed, they always are coarser textured than everything else. But that's a product of events stripping stuff. So the finer particles have been moved out. And it really, this E, there's a couple of things that control where that E is. I mean, that E could be way down here. It really has to do with the texture of the material and the structure of the material above it, and the organic matter. Because that's going to sort of control the flow of water through that system. Now, it's also, depending upon what's up here, it's also going to control the mineralogy of that. If I have an acidic material, I'm going to be moving acids through this, which are going to weather away things a lot faster than if it wasn't acidic. So that will also have control on where that E is. Now, the reason that E tends to be coarser textured is the result. It's not because it started coarser textured. It's been stripped out. All the fines have been stripped out of it, and so it becomes a coarser horizon. Does that make sense to everybody? Kind of. Okay, imagine I start with a soil. Okay, here's the top of my soil up here, the bottom up here. Okay, and we're basically looking, this line represents clay content, okay, throughout my soil. Okay, and when I start this soil, this entire soil, from top to bottom, is a sea horizon. Does that make sense? Undifferentiated material. Okay, the process that we're going to watch now is it's just going to be rainwater, nothing else. Okay, it starts to rain at the surface. Okay, that water is going to percolate in, and it's going to start entraining clay. Okay, imagine this soil. This soil started as a silt. No, it's a loam. Okay, so it's a mix of all different kinds of textures: sand, silts, and clays. Okay, this water starts moving through, and it's going to start entraining the clays first. Right? Does that make sense? So those clays are going to start moving down, which means my clay bulge at the top, my clay is going to go down, and I'm going to have an accumulation of clays farther down. But then I'm going to get back to this sort of straight line. Does that make sense? Right? Now that water is going to keep moving through this system. Okay? And I'm also, importantly, I'm also going to have stuff starting to grow on this. Okay? If I have stuff starting to grow, I'm going to start seeing an accumulation of organic matter. Okay? And that organic matter is going to start slowing down the loss of those clays, because it's going to hold it in place. Which means this curve up here is not, the top of this curve is not going to shift this way anymore. But the water is still flowing through the system, so I'm going to start seeing this kind of pattern as this zone here where the roots aren't is going to lose clays preferentially versus the stuff that's at the top. Give me a couple more years, and I'm going to start having a bulge that looks like that. Does that make sense to everybody? Kind of-ish. If you have questions about this, and this is actually pretty important, if you have questions about this, come talk to me. Okay? And we will, in fact, be talking about this week when we go out to the field. Okay, good?
What did you say about iron?
Iron is sort of the same thing. Iron is soluble, though. If you think about Fe oxide, so rust. Okay, iron. You take a nail, you put it outside and let it rain on it. What's going to happen to that nail if it's made out of iron? The water is going to move into, it's going to saturate it, and what's going to happen is the system's going to go anaerobic. Okay? It turns out that there are organisms, and we will talk about this as well, there are organisms out there that want to respire. They still want to breathe, but if there's no oxygen, they can't use oxygen. So unlike us, who can't use another element for respiration, these organisms can use iron for respiration. And in the process, they reduce it. Okay? Reduced iron, Fe+2 versus Fe+3. And we'll talk about this. This has very distinct colors, which is actually very important for us. Fe+2 is the result of these organisms using iron for respiration. Okay? The interesting thing about Fe+2 is that it's soluble. Fe+3, iron, that's what we're used to, doesn't dissolve in water. But Fe+2 can. And if Fe+ can, and it's present at the soil surface, and it's present up there, and the water moves through the system, that's going to move that iron down through the system. Right? Now, interestingly enough, the minute that reduced iron gets into the presence of oxygen without microbes, it oxidizes. It turns back into Fe+3, like that. And it has a very distinct color, which is red. And it's insoluble, which means it's accumulating. Okay? Starts to rain, the rainwater moves down here. If it doesn't rain enough to saturate the system, there's going to be pockets of oxygen down here. The minute that iron hits that oxygen, it's going to oxidize, and it's going to be deposited down here. The same, in essence, the same way as the clay is, conceptually the same way the clay is. Clay is actually being entrained. It's not dissolving. Okay, though that we'll talk about that a little bit. In some cases it does dissolve, but the iron is dissolving, being moved to an oxygenated area, and it's oxidizing. And then that, in essence, is why we have rust. The rust is the product of this reduction of the iron and then its reoxidation. Does that sound familiar? Is that cool fact? Ooh, neat. No. And actually, you'll see the rust in the soil. This will be very diagnostic. We can use the patterns of the rust to tell us where the water is. Okay, we're stopping lecture there. Exercise. Before you guys come into lecture on Wednesday, I want you to go outside, take a look at some of these monoliths. There's monoliths in the lab as well as in the hallway. And there's actually some on the 6th floor and the 7th floor. Take a look at one of these soils. Figure out a soil that you think is cool. Look at the features in that soil, and it's going to have some of this horizon nomenclature. Take a look at it. Give me a paragraph description about how you think this soil is behaving and why. Okay? Okay, where it came from, lots of different things that you can be putting in there. You don't have to put everything in there, but basically a paragraph. You're going to be handing it in, handwritten. I'm not going to be looking for plagiarism here. Handwritten and handed to me on Wednesday morning. Okay? Cool beans? All right, be free.